All right, hey everybody. Welcome to the the last lesson in lesson one. So this is all chapter 4. So this last section involves word problems, and I'm not exactly sure about the organization of this particular chapter. It seems like it's they just throw a ton of word problems at you, and I'm not sure if you actually are able to solve a lot of them. Lots of them involve things that we haven't talked about so far. So we're gonna stick to a smaller set of them. But one really nice thing about this chapter is that it talks about solving word problems, the general methodology of solving word problems. And so I thought we could do it. So on the notes, I've transcribed a few problems, and shortly I'm going to go through, essentially, you're going to watch me do problem solving on the fly. I haven't prepared notes for solving the particular problems because I want you to hear what kind of things go through a person's head while they solve problems, okay? So the objectives are, we're going to, at the end of this, you should hopefully be able to describe what a model is. You should be able to list the 4 steps for algebraic modeling. I want you to identify a variable in a word problem. That's the big step. And then we want you to be able to write expressions which describe the various clues that you're given. So algebraic expressions describing the clues. And then we will be able to write, and then the second to last step is you'll be able to write an equation, which we call a model. Maybe I should write that. A model. Using expressions and describing the overall clues, the relationships between all the things you don't know in terms of them. And then you just solve them. So overall, we want you to be able to solve simple word problems using algebra. So we're going to talk about the general theory behind that. First off, before we go on, what do we mean by model? What do you think when you think of the word model? Somebody tells you a model. There's the phrase mathematical model. You can think about a little toy models, like you can make a model Gundam, or you can make a model train or a model car. The thing about models is they're simplified representations and of relationships. Okay. So if you have a model car, it's got a simplified. It doesn't have a working motor or anything. Everything's smaller and made of plastic. But there you have all the basic relationships to the parts. The door is attached to the door frame. I don't know how cars work. Anyway, so the same thing in math. So what you might have overall, especially in a word problem, is you're given a complicated system where there's a whole bunch of interacting parts that are related to one another in complicated ways. And what we're going to do is we're going to ignore, maybe you'll get a problem about pigs, or a problem about chickens, or a problem about money, or something like that. And we're going to reduce all of the complexity down to a few mathematical expressions, which we then say, okay, so these are not the actual relationships, but what they are is they're a model of their relationships, a mathematical representation of those relationships, which we can then solve. So a big aspect to doing this is going from talking about complicated relationships into essentially, I'm expressing everything in these relationships in terms of these simple models, or something like that, right? And so it's a little bit, this oversimplification as a step seems frustrating to a lot of people. But the purpose here, one of the strengths of mathematics is that in some situations, by simplifying the relationships down to a model, we can actually figure out an answer. And so it's so bear with us. So when we're talking about a model, in this case, often we'll be talking about a single equation that represents all of the different complicated relationships. I just wanted to get that out of the way before we started too much. You'll get a better sense of what a model is as I narrate. Okay, so somebody gives you a word problem. In real life, word problems are sometimes encountered in real life. Like somebody will say, I'm building a house. How many boards do I need? How many nails do I need? And these are definitely things that you can solve using mathematics. Other times, you know, what color should my house be? I don't know. That's not something you can answer in mathematics. Life tends to be fairly complicated, and often there's more than one solution or no one good solution. On the other hand, the nice thing about math is that I will never give you, and in any of your courses, you'll never be given a problem that can't be solved using simple mathematics. And so, essentially, I'm looking for a number. What is this number? So you're looking for a specific number that satisfies all of the descriptions. In other words, word problems are a type of riddle. Unlike the regular problems of life, there is a solution, and usually it's one simple number. Okay? So, so the type of problem we're actually doing is really neat because the history goes back. As long as people have been writing words down, they've been describing the mathematics to solve these problems. And the interesting thing, if you go back to the ancient like you know, the ancient Egyptians or the ancient Babylonians, they had mathematical recipes to solve all their problems. So, for instance, they'd be like, okay, Ishtar wants, you know, to feed their horses. They have 12 cattle and 7 horses, and then so to figure out the number of bales of hay that Ishtar needs to buy at the market, add the number of cattle to the number of horses, and then multiply that number by 4, and subtract 1, and then divide that number by 3, or something like that. And so there would be a specific recipe for every application, which went from building pyramids to building ziggurats to, you know, baking loaves of bread. Anyway, long story short, the advent of algebra as a technology actually kind of revolutionized these problems, because what people saw is instead of having to memorize a different recipe for every situation, you know, where you have like, okay, we're going to talk about bread. Here's the recipe for the amount of loaves. You know, if I want to make 17 loaves of bread, how much flour do I need? Add 7. Subtract 6 by the number of people at your party. Instead of all this, what algebra allowed us to do is then represent all of the different parts of the situation using mathematical notation, and then use the rules of algebra to determine the solution. So it was a unified way of solving these problems, which then didn't require people to memorize 100,000 different essentially procedures for every situation. Instead, they just needed to know how to use an algebraic problem-solving method. So essentially, that's what we're teaching you today, this algebraic problem-solving method. It's absolutely fantastic. Okay, so essentially there are 4 steps. Okay, so before I go on, there is a system for word problems. There's always essentially three different pieces of information you're given. One of them is a set of clues. Okay. So you might say, oh, your fence has to be twice as long as your other fence. Or you might say, hey, the price of this has to be 4 times the number of the price of that. There are clues. In addition to that, there's a relationship between these clues. Okay? And then finally, there's an overall question, a number that you want to find. Okay? And so the idea here is we're going to use algebra. So, okay, so part of solving one of these, essentially these word problem riddles, is figuring out, parsing the paragraph to figure out what the clues are, what the relationship is, and then what the question we're trying to answer is. Okay? So there's a big part of this that comes down to interpretation. So sometimes it's actually tricky to interpret a question, and you find yourself spending a little bit of time interpreting it. That time isn't lost, because what it boils down to is you're going to treat these three aspects of it differently. So step one of how to solve a word problem is you want to assign a variable. Essentially, you choose a letter, X or T or N or M, just a letter, and you want this to be the answer to the question. In more advanced cases, sometimes the variable you're assigning isn't the answer to the question, but the answer to the question can easily be found using that value. But the idea is we're going to solve algebraically for that value. Okay, so essentially you want to say, okay, instead of how many pigs do I need, I'm going to say X. I'm going to represent the answer to the question, how many pigs do I need, by the letter X. Okay. The next step is to interpret the clues. So for each clue, sometimes the clues are called unknowns. Write an expression relating the value of X to the clue. We'll get in a little bit what this means in when we start doing them, but essentially the next step is to figure out what the clues are. So each time in any of these word problems there's a list of clues, and all of them are kind of related to one another, or all of them are related to the value of X. And so you want to represent each of these clues as an algebraic expression. And then there's always a key relationship. The relationship is, sometimes it's given, sometimes it's implied using a word, but the relationship is a relationship between the unknowns. It's a relationship between the clues. Okay? You want to represent this as an equation. In other words, we're setting some expressions equal to each other. So we call this representation of the relationship between these clues. We call that the model. Okay? And then step 4 is I put it all together. You have the model, which is the relationship between each clues. You have each clue represented as an expression of X, so then you solve the equation for X, which is the solution. How about a secret step 5? You can always test. So one thing it's helpful to do is once you think you have a number that's a solution, test the number to see if it satisfies all the clues. Okay? So that's the overview. First you assign the value X, then you interpret each clue. Sometimes these intermediate steps, as an aside, sometimes this part of it is easier drawing pictures or writing out a table. It depends on the question. So let's try some of these questions and see if we can solve them. Like I said, I haven't worked out the solution to them beforehand because I want you to see me problem solving live. I'm not a bad problem solver. Okay. A student wants a final average of 75% on 3 exams. His grades on the first 2 exams are 65, and 82. What grade must he achieve on the third exam? Okay, so step 1, I want to choose what my variable is, identify my variable. The question they're asking is the grade on the third exam. So I'll call grade on third exam, I'll call that X. I could have called it G, doesn't matter. You just choose a letter. Okay. And now the clues. Okay, so a student wants a final average of 75%. Is that a clue, or is that a relationship between other things? That seems to be like a thing you determine after the fact. So that's kind of like a relationship. His grades on the first 2 exams are 65 and 82. Those seem like clues. Grade on first is 65%. Grade on second is 82%. Let me get those percentages out. I'll just understand that these are percents. So these are expressions. They're mathematical expression. A number is a type of polynomial, remember? Okay. So this part here, these are clues. And this part here is a relationship between the clues. What's the relationship? Well, if I have 3 tests, and I want to figure out what their average is, I add together the grade on each test and I divide it by the number of tests. Right? So it seems like, in this case, the grade on the first test is 65, the grade on the second test is 82, the grade on the third test is, I don't know what that is yet, divide by 3, and that's equal to 75. So now this is the I've just done the third step. Now I need to do the fourth step and evaluate, solve it for x. So first I'm going to multiply by 3. Multiply both sides by 3. 75 times 3. 225. And now I'm going to subtract 65 from both sides. And now I'm going to subtract 82 from both sides. X should be 78%. Okay, so let's test it. 78 plus 65 plus 82. The average between all 3 of these is equal to 78 plus 65 plus 82 divided by 3, 75%. Do you see how that works? Essentially, the trick here is not to get overwhelmed with the different aspects to a word problem. You're being bombarded with information. But in these classes, it's less complicated than real life. Essentially, there's always a question we want to answer. There's always clues given, and then there's always a relationship between the clues. And you're going to put them all together mathematically. So, incidentally, this part, that's called the model. Okay, let's move to the next question. Oh wow, it's a mathy one. The sum of the perimeter of a square and a triangle is 24 meters. The edges of the triangle are each 1 meter longer than those of the square. How long are the edges of the square? Okay, well, you know what? I think before we even start problem solving, it might be helpful just to draw a triangle and a square. Also, I think that they meant that this should be an equilateral triangle. That's an important clue. I copied this straight out of the book, and they didn't say it was an equilateral triangle, but they had a drawing of an equilateral triangle. Sometimes they don't tell you enough, and you need to raise your hand, and you need to say, I think this word problem is bad. Okay, so it's an equilateral triangle. All right. So what's the thing we're trying to figure out? It's how long are the edges of the square? Okay, so uh, let's assign that a variable, x. All right. To help us out, I think we should start labeling this diagram. It's a square, and that means that the sides are all the same length. The triangle, it's going to have a different length and height than the square does, so I'll call its length t, just to represent that they have the same length here. Okay. All right, now it's time to look at clues. The sum of the perimeter of the square and an equilateral triangle is 24 meters. It seems to me like that is a relationship between the edges of the squares and the edges of the triangle. So that's probably the relationship. The edge of the triangle are each 1 meter longer than those of the square. Ah, that's a clue. All right, so it's saying that the length of the edge is the length of the edge of a square plus 1. So let me actually replace in my drawing. I'll replace these with x plus 1. All right, well that goes my clue. Now I've got to write out, I've got to make my model. I have to represent the relationship as algebraically. So it says the sum of the perimeter of the square and an equilateral triangle is 24 meters. Okay, so sum means add together. Perimeter, that means that you add up all the lengths on the outsides. So for the square, the perimeter is going to be x plus x plus x plus x. And for the triangle, incorporating this clue into it, the triangle should be x plus 1 plus x plus 1 plus x plus 1. All right? And that overall is 24 meters. So let me rewrite this as 4x and 3x plus 1, which should make total sense to you. So now I need to solve this for x. So I'm going to expand it out. And I'll simplify it. 7x plus 3 is equal to 24. And now I'm going to subtract 3 from both sides. 7x is equal to 21, and I'll divide by 7. So x should be 3. Well, let's test it. If that's the case, then it should be 3, 3, 3, 3, and the triangle should be 1 more than 3. 4, 4, 4. Let's get out my calculator. 3 plus 3 plus 3 plus 3 plus 4 plus 4 plus 4. 24. Hooray. Hey, does that make sense? Problem solving in this mode, it won't be able to solve any problem in the world, but it will be able to solve the types of problems you see in math classes, so it's helpful to use it. All right, here's a fun one. I have 144 change in my pocket. If there's an equal numbers of pennies, dimes, and quarters, how many of each coin do I have in my pocket? So I can't spell out enough of how useful it is to like draw a picture as you're thinking about things. Drawing pictures helps you you don't think things through. Okay, so what's the question? How many of each coin do I have in my pocket? Well, okay, it's a little bit strange. Well, I mean, if I have P pennies, I could call, okay, number of pennies. And number of dimes. I'm going to have trouble writing this. P pennies and Q's quarters. Okay. So that's the I guess there are 3 variables. Weird. All right. Now, what's the clue? Okay, so what's the clue and what's the relationship? Seems to me like I have 144. That's a relationship between all of the types of money in my pocket. So this is the relationship. And these ones are the clues. If there is an equal number of pennies, dimes, and quarters. Okay. So the number of pennies and dimes and quarters is all equal. So the number of dimes is the same number as the number of quarters, is the same number as the number of pennies. So I guess let's over here, let's write that there are Q quarters and Q dimes and Q pennies. Well, that's interesting. So that's the relationship. I mean, those are the 3 clues. There's the same number of dimes as quarters, same number as pennies as quarters. All right, let's write out the relationship. 144 change in my pocket. That means that if I add up the monetary sum of each of these, it's $1.44. Well, okay, so the monetary value of a quarter is 25 cents. So if I add that to the monetary value of a dime, and if I add that to the monetary value of a penny, then this is the amount of money in quarters. This is the amount of money in dimes. Whoa, I forgot nickels. Oh, geez. How could I forget nickels? Okay, so they're Q nickels. Alright, and then 0.05 nickels. And there are Q nickels. So this is the amount of money in quarters. This one's the amount of money in dimes. This is the number of money in pennies. This is the number of nickels. And if you add them all up, you get 1.44. Well, this is a polynomial involving the variable q. So I just solve it like any polynomial. The next step is to simplify it. Let me combine these two together. I'll just do it. So it's 0.35 times q. And these two together are 0.06 times q. If you add those together, you get 144. Combine these two together, and you get 0.41 q is equal to 1.44. I'm going to divide both sides by 0.41. What? 0.25 plus 0.1 plus 0.01 plus 0.05. 1.44 divided by 0.41. What on earth? Hold on. Wait, hold on. Oh, you know what? It doesn't say they're nickels. I made a mistake. So I got a weird answer, long story short, and I said I should probably get a whole number of coins. So let's look at these clues again. Pennies, dimes, quarters. It doesn't say anything about nickels. So I probably shouldn't have added this nickel line. And these need to go away. And so when you add it up, 0.01, it's 0.36. All right. 1.44 divided by 0.36. 4. That's the amount of dimes, quarters, and nickels. Let's test it. Uh, 0.25 times 4 is $1. Dimes, 0.1 times 4 is 40 cents. 0.01 times 4 is 4 cents. You add them all together, you get 1.44. Check mark. Got the right answer. All right. Next question. A 10-ton truck and a 12-ton truck both deliver gravel to a construction site. If the smaller truck makes 3 more trips than the larger truck, how many trips does each truck make to deliver 142 tons of gravel? All right. So just like in the last case, there's actually, when they ask the question, they're asking about two different numbers, and there's a relationship between them. So how do we assign the variable? Well, we can do it either way. You just have to choose one of them. Small truck. Big truck. How about if we make the big truck, the number of trips the big truck takes, we'll call that x. This is a type of problem where it's sometimes helpful to write out equations or a table. How many trips does the big truck take? We get a clue about that. The smaller truck makes 3 more trips than the bigger truck. So the small truck must make x plus 3 trips. Okay. So where in this is the relationship between the different terms? 10-ton truck, 12-ton truck. So one of the trucks brings 10 tons in at every trip, and the other brings 12 tons in every trip. The smaller truck makes 3 more trips than the larger truck, and they're going to deliver 140 tons of gravel. Okay. Well, each time a small truck makes a trip, it delivers 10 tons of gravel. So the amount of gravel from small truck in total will be 10 tons times the number of trips. The amount of gravel the big truck brings overall is 12 tons times the number of trips. And the relationship between them is the gravel truck, the small one plus the big one is equal to 140 in total. So now we have to simplify. There's our model. You might ask why it's called a model. This is a great example of a model in that it's oversimplifying things. Like, what's it oversimplifying? I thought everything was straightforward. We're assuming when we are writing all this out that both trucks deliver reliably 10 tons and 12 tons. What if one is overfilled? What if one of them reliably has less than its limit of gravel in it? We're not accounting for that. We're assuming that it's simpler than it actually is. So combine these together, so it's 22x is equal to 140. Subtract 30 from both sides. Divide by 22. The small truck makes 5 trips, and the big truck makes 5 trips. The small one makes 8 trips. Okay. So let's test it. If the big truck makes 5 trips, then it delivers 60. And if the small truck makes 8 trips, it delivers 80. And you add those together, 140. Okay, this is the last question. Farmer Bob. Okay, so at this point in the game, you might be like, you might notice something, which is that our problem-solving technique, where we break the question down into pieces of information and try to parse them, our technique is suddenly getting a little bit more difficult to apply. So in the last question, the relationship between all the terms was smeared out all over the word problem. The whole word problem from start to end had little bits of information that described their relationship. And the clues were buried inside of those. And also our deciding which one to apply the variable to, which one to call x, was also kind of an issue. There is an art to solving these word problems. If it was super straightforward, if a robot could do it, then there would be no need for people. Parsing the information and so interpreting the information, trying to recognize what are clues, what's the big overall relationship, that's something that you have to learn to do. So be patient with yourself when you do. I'm sure you can get on a hold of this. Millions of humans over the history of teaching have learned to do these questions, and you can too. It just takes a little bit of patience and practice. Okay, the last question. Farmer Bob, oh, and it comes with a little picture. That's cute. Farmer Bob needs to build a rectangular fence to hold his chickens, and he needs it to surround 28 square meters. His designated chicken pen has a chicken coop which is 3 meters deep. There it is, along with a square area out front, which is as wide as the chicken coop is. How wide should the chicken coop be? So I don't know, maybe Farmer Bob is like, well, I read in a book that every chicken needs 1 square meter of total living area. That includes the pecking yard and the coop. And he found out that you can buy a 3 meter wide chicken coop that can be as long as it needs to be. And he found out that the best shape for a chicken pen is a square. And so he's like, hey, how much fence do we need? What are the dimensions of this fence? Okay, so what are we given? In this circumstance, you're given a diagram, and that's actually pretty helpful to parse things. And we can start analyzing this question by drawing on the diagram. How wide should the chicken coop be? Okay, that's the question we're trying to answer. Let's assign it a variable. Okay, so I guess that's this dimension. Okay. All right. His designated chicken pen has a chicken coop which is 3 meters deep. I guess that's already been drawn, along with a square area. So it's told us that this area here is a square. So that's a clue. The clue in that says, well, okay, so it has to have the same height as the width as the chicken coop, and then this length here has to be the same value because it's a square. Okay, so those are the clues. This to this is clues about the chicken pen. Okay. Now I go to the relationship. I want to build a model of this. It needs to be a total of 28 square meters. How do we talk about that? Well, that's going to be the width here, which is 3 plus x, times the height, which is, I guess, x. So the relationship between these sides is that x times 3 plus x is equal to 28. So I can rewrite this as 3x plus x squared is equal to 28. Oh, look. So this becomes x squared plus 3x minus 28 is equal to 0. The width of the chicken coop needs to solve this equation. I'm trying to find rather this equation tells me what the width of the chicken coop needs to be. So let's put it in the quadratic formula. Essentially, I'm looking for the solution of a quadratic equation when it equals 0. That means I can use the quadratic formula. A is equal to 1, b is equal to 3, c is equal to minus 28. So it's minus b plus or minus square root b squared minus 4 times a times b, all divided by 2 times a. Let's simplify this. Get out my calculator. 9 plus 28 times 4. 1, 1, 2. Why is it a plus? Why isn't it a minus? Remember, there's a negative sign here and a negative sign here, so it becomes positive. Minus 3 plus or minus square root 121 over 2. So it's minus 3 plus or minus, okay, just take the square root of 121. That's 11. So the answers are either minus 3 minus 11 over 2 or minus 3 plus 11 over 2. This becomes minus 14 over 2, that's minus 7, and this one becomes 8. 8 over 2, which is equal to 4. So I have two answers. Will they both work? This is another aspect to the idea of calling an expression like this a model, which is to say that we've oversimplified things, and so we have to apply what the equation tells us in an intelligent way. Does the answer we've got make contextual sense? So here we have two numbers, both of which, if I plug them into this equation, right? If I plug either of them into this equation, you get the answer 0. So fine, they both solve it. In the context of dimensions of the chicken coop, 4 is a fine number. That makes lots of sense. Does minus 7 make sense? Can I have a width that's minus 7 meters long? The math says, hey, this works, but contextually, this answer doesn't make sense. So, I mean, it's possible to have two answers to these questions, but in this case, there's no answer to the question. Only one. So x is equal to 4 is the only answer. Okay, so that's it for now. Actually, you know what? It's time for a medicine wheel. There are different aspects to the strategy. I noticed that the medicine wheel for this sign, it comes from a different chapter, but so this is the medicine wheel straight out of the book. I've used a slightly different terminology when we've talked, but it should all be there. So here's the overall idea. When you get a word problem, it's a ton of information that's all dumped verbally. And so a big aspect of solving a word problem is parsing it, okay? Which means interpreting it. Parsing word problems isn't easy, but our 4-step problem-solving strategy gives us a scaffold to help parse us. So the first step involves identifying the variable. We're going to assign the solution to the problem, the question they're asking, or at least one of them. Sometimes they ask for 2 numbers. We're going to assign that a variable. Okay, so we're going to say that's the value x. I don't know it. The rest of the problem essentially is a whole bunch of relationships between that value and other values. Some of these values I've classified as clues, which is to say, like us saying, hey, the chicken coop is 3 plus 3 longer than its size, its width, something like that. Okay? So each of these is a statement relating different numbers, relating different values, and it's also kind of a constraint on what the solution has to do. The solution has to do this, and the solution has to do that. We write each of those as an expression, a mathematical expression. Okay. And then there's the model stage. There is an overall relationship that all these smaller relationships have to satisfy. I need my fence to be a total area 24 squared. I need the total perimeter to be 18. Whatever, something like that, right? Talking about totals. Relationships between the clues, the smaller bits of information. So you identify the variable, you write out the expressions in terms of this variable, and then you use what's given about these clues to describe the situation, describe the overall relationship between things. Doing so is equivalent to setting up a single equation in terms of our variable that we started with. The result is a single equation that we can then solve algebraically. And that's the idea. There's more than one technique and there's more than one route through these word problems. If you've been taught another one and you're comfortable with it, I don't care which one you use. But often when people approach these word problems, they kind of freeze up because it's big and weird. Okay, well that's it for this lesson. Lesson 2 starts next.